We know that if a graph has an Eulerian cycle, the degree of every vertex has to be even. But is the converse true? If we are given a connected graph and the degree of every vertex is given to be even, does that mean that the graph must have an Eulerian cycle? Now, in general, in logic, if we have a statement A implying statement B, it's not necessarily true that the statement B has to imply statement A. So, for example, if I tell you that something is a given figure is a square, you can conclude that this figure must be a rectangle. But just because it's given to be a rectangle doesn't mean that it necessarily has to be a square. Every square is a rectangle, but not every rectangle is a square. So here I've drawn a new graph where the degree of every vertex is even, and you can verify this. The degree of every vertex in this graph is either a 2 or a 4. So we want to explore the question of whether there must be an Eulerian cycle in this graph or not. And since we don't seem to have a clear idea of how to proceed, let's just try to construct an Eulerian cycle by starting from a random vertex in this graph, let's say this one, and let me just pick a random direction, and I'm not going to plan my trip in any uh, particular way, so I'm just going to make a random choice whenever I come to an intersection where there are multiple options. I'm just going to pick a random edge out of those possibilities and just see what happens if I just keep walking randomly. Till what point can I keep doing that? So at this point it looks like I have no choices left, and I come back to my starting vertex and I got trapped. So since my choices were random, they were not planned out, I didn't get an Eulerian cycle, and maybe even if I had tried to plan my route, it may not have been possible to get an Eulerian cycle. That's what we want to find out. Is it always possible to get an Eulerian cycle if the graph has every vertex with an even degree? Now, since I didn't get an Eulerian cycle at the end, I missed out on some of the edges. I'm going to try to backtrack from my final position here, and I'm just going to try and backtrack and see what was the last point where I made a wrong turn. And it looks like I made a wrong turn here. By going left here, I ended up getting back to the start vertex and getting trapped there. Whereas if I had chosen to go right here, I would have kept going along these three edges and would have covered them as well before coming back to this vertex. And had I done that, then these three edges would have also become part of my original tour, and including these three vertices, if I had got back to my starting point, I would have at least got a bigger cycle. It would still not have been an Eulerian cycle since I would have still left out three more edges here, but at least it would have been a better or a closer approximation to an Eulerian cycle. Now, if I think carefully about it, I might notice that at this vertex where I made a mistake, the last point where I made a mistake, the degree of this vertex was even in the original graph, and even during my tour I ended up using an even number of edges that are incident on this vertex. So this vertex had a degree of 4 and I ended up using 2 of those edges. I did not end up using these 2 edges. So what I can do is I can pretend that I am backtracking from my final location, and I can pretend pausing my tour when I reach this vertex. So imagine I had a recording of my whole tour. So I take the recording up to the point I reach this vertex from the start vertex, and then I embark on a mini walk. I embark on a mini walk along those unused edges which I had missed out in my original walk, And my claim is that if I embark on a mini walk starting from this vertex, I have to come back to this vertex at the end of the mini walk. Now, why is that? Well, because this vertex originally had an even degree and I had used an even number of edges in my original walk, that means the number of unused edges out of it would have also remained even, an even number. So if I began a mini walk along those unused edges, because every other vertex of the graph would have had an even degree, and even if some of these vertices had, maybe there were other connections from here to other parts of the graph, and some of those connections might have been some of those edges might have been used, but it would still I would still have the guarantee that there would be an even number of unused edges out of every vertex in the graph, right? So even if I don't create an Eulerian cycle, I am still guaranteed that if I look at all the remaining edges and the remaining vertices on which those edges are incident, those remaining vertices must have an even number of unused edges for each of them, right? So if I begin my mini walk from this kind of a vertex, I'm guaranteed that I won't get trapped anywhere else except after coming back to that detour vertex. So given this property, it looks like I can always build a mini walk like this by backtracking, and I will get a cycle, a small cycle making up my mini walk, and I can take that small cycle and I can insert it into my original walk, making my original walk longer. Now, even if I do this here, it's clear that I'm still missing out on some edges. So what I will do is I will pretend that my new walk now has these blue edges also. So I'm going to keep backtracking from there and go back again to a vertex where I made a mistake. So what was the mistake I made at this vertex? Well, I was coming from this direction, and instead of going along one of these edges, I chose to go along this edge here. So what if I again treat this vertex as a detour vertex and I start a mini walk along one of its unused edges? Since this vertex had an even degree at the beginning, even if I subtract out the used edges from it, the number of unused edges has to be an even number, and that must be true for every other vertex in the graph. So if I begin a mini walk again from here and just pick one of those edges randomly, the only place where I can end up is back at that detour vertex. There is no other place I could get trapped, because every vertex in the graph had an even degree at the beginning, and it continues to have an even number of unused edges at this point. So once I come back to this vertex, I can again take this mini walk and insert it into my existing walk up to that point. And if I do that, now suddenly I find that I have covered every edge in my graph as part of this tour. So my overall tour now looks something like this. I started from here, I went like this, and this is the point I reach this detour vertex. I follow the three edges here, I continue like this, I reach another detour vertex, and again I follow the mini walk that I had constructed, and then I get back to the start vertex, and by doing so I have covered every single edge of the graph as part of this cycle. And the kind of reasoning we looked at here seems to apply in general to any kind of graph with an even degree. As long as the graph is connected, it looks like we can always conduct these mini walks while backtracking to keep extending our original walk more and more, so that ultimately we will get an Eulerian cycle at the end. So let's just do one more example of this with the diagram we had seen earlier. We had checked that all the vertices in this graph have an even degree, but we want to find out if there is an Eulerian cycle in this graph or not. And I'm going to test out the method we just constructed by starting from a random vertex and I'm just going to do a random walk here. In fact, I'm going to just deliberately avoid some edges. I'm going to deliberately make some mistakes so that we can come back and see if those mistakes can be fixed. So I have now come back to my starting vertex, and I see that I have excluded a bunch of edges over here. So let's see if we can again follow the process we had followed for the previous graph. I'm going to start from this vertex. After ending there, I'm going to start backtracking from there and come to a vertex where I made a so-called mistake. Okay, and the mistake I made was I chose to go along this direction instead of choosing one of these unused edges. So what I will do is I will try to rectify my walk by starting a detour from here and following one of those unused edges and just see where I end up. So if I keep following this unused edge, I get back to this vertex which also has an unused edge. Keep walking along like that, cover this edge. Again I get to this vertex. I had this vertex had an even degree, and two of its edges were used, but that means that there was an even number of edges that were unused. So whenever I get to an intermediate vertex like this, I should be able to find an unused edge out of it. Same thing applies to this vertex, and I just continue like that, and lo and behold, I'm back at this detour vertex after conducting this mini walk, grabbing another cycle in the process. And now if I look at this whole, if I just stare at this graph, I see that I have covered all edges. All I had to do was to take this mini walk and insert it or splice it into my original walk so that I get a complete Eulerian cycle. So let me use a different color to construct that cycle. So I started like this, I went like that, I went like that, and this is where I had made a wrong turn. Now instead of going in that direction, I'm just going to take all the edges of the mini walk I had, cover them, and then go in that direction, and by doing so I get back to the start vertex, covering every single edge in the graph, and this gives me an Eulerian cycle. So it does seem that the answer to this question is a yes. If there is, if you're given an undirected graph that is connected and you're given that the degree of every vertex is even, yes, it must have an Eulerian cycle because the process that we followed to build that cycle seems infallible. So it looks like the implication goes both ways. If there is an Eulerian cycle in a graph, then every vertex in that graph must have an even degree, and if every vertex has an even degree, then that graph must have an Eulerian cycle. And remember, we are assuming that the graph is connected because there is a slight caveat here that it's possible for a graph to not be connected and still have an Eulerian cycle, as we saw in a previous video. So this graph is not connected, but it does have an Eulerian cycle in it. But in general, we can say that a connected graph will have an Eulerian cycle if and only if the degree of every vertex is even. So this is definitely true. And in addition to this, we can say that this statement also applies to graphs that may not be connected, but at least all the edges of such a graph have to be part of the same connected component. And by the way, the phrase if and only if means that the implication goes both ways. So if I say A if and only if B, that means A implies B and B implies A. So a connected graph has an Eulerian cycle. This implies that the degree of every vertex must be even, and if the degree of every vertex is even in this connected graph, then it must have an Eulerian cycle.